Hi everyone, here's a little bit of information about your mock exam this morning. The first three here, these are things that you should be able to just learn out of your books quite easily and work them out from the thing at the top there. Okay, so I'm not going to go over these ones. But what I will do is the analytical part for you. If we look first at the links that I've sent, here's the heartbeat data. So this is just the data that relates to the heartbeat, and this is a plot of those distributions. And we've got histogram, QQ plot, and a density plot of the same data. Okay. Now, to me, looking at the histogram, these dots should all be clustered along this line if the data is distributed normally. And there seems to be one outlier, and that's confirmed by the histogram. This one at the end here, sitting on its own, and also by the density plot. So there's a question there as to whether there's an outlier. Perhaps that if that was removed, this would be a normally distributed sample. If we look at the no heartbeat babies plot, this one here, this is just of the column of data for the babies who heard the heartbeat. Now if we look at the QQ plot, we can see there's systematic deviations away from the QQ plot normality line here, okay? And when it's like this, it suggests that there's too much data away in the tails of the distribution. See, this here is it's sort of more flattened out. It's a platykurtic distribution, right? And we can see that a little bit also in the density plot. There's too much data away out in the tail. So this is quite strongly not normal population. So thinking about our comparison of our means that we need to do for this study, we're comparing the weight gain between a group of babies that didn't hear the mother's heartbeat and a group of babies that did hear the heartbeat. We want to know if those average gain in weight is different between the two groups. That is interesting. And so we come to the second part now, so we have to look now at our data. So what I would do here is copy, here's our Salk data set, you see, and we copy the data in for the heartbeat and the no heartbeat data. You see these things here, this means not available, we haven't got data. Okay, so the groups are unbalanced. There were 21 or 20 babies in that listen to the heartbeat, and there's more than 20, 36, who were in the no heartbeat group. Okay, you might be tempted just to include the same number in each group, but this not available thing means that we're able to include unbalanced data, so we can have 36 in one group and 21 in the other group. So we should include all the data, including the not available tag. So when I put that into our data here, there's the data I've already pasted it in. There's my NAs at the bottom. And I've been careful to make sure that the heartbeat group is the first column and the no heartbeat group is the second column. I'm going to do a two-sided test because I've got no prior expectation of which group is going to be the heavier. There's no theoretical reasons that it's definitely going to turn out one way, because it's usually safest to do a two-sided test. It's more conservative. The ordering of these things just means that we're going to subtract column 2 from column 1, and that's the value that the test is going to compare. It's going to compare the differences between the means of the two columns, are actually the medians, because we're going to use the Mann-Whitney test. Because of the suspicion that the two samples were not normally distributed, we sort of taking a risk by using a normal t-test here, an ordinary t-test. The observations are not paired because there's the baby's only in one group or the other group, and we're going to test the difference of means to 0. That means that the baby group, the heartbeat baby group, is expected to have the same weight gain as the no heartbeat baby group, on the assumption that there's no difference. Okay? I'm going to display a box plot, and I'm going to put some titles in. This is all study, isn't it? So I'll put Salk in there, which is the guy that did it. The Y, label the y-axis, that's the dependent variable, that's weight gain, isn't it? Weight change. And on the bottom here we've got the group that they were in. And then compute that. So down the bottom. Okay, we've got a nice little plot there. Looks like there's a few outliers, but remember that is because, see these guys here, that's because we've got this platykurtic distribution. But it seems to be symmetric, so that's really good. Now what's our answer? Turns out that our Wilcoxon test says that the mean gain and weight of the babies is significantly different. Okay, so it matters which way round the babies have their weights measured. Okay. This particular display doesn't calculate the mean values. You can either do that in Excel if you want to. That would be one way of doing it, which is equals average there of all the relevant ones, like so. That's the easy way to do it. So the average weight there, so you can do that. Or, actually cheating a bit, you can recalculate this with the t-test. And that also gives you descriptive statistics for the data. Now we have the mean and so on of these data sets. And standard deviations are computed for both of these things. Okay? So so it looks like one group of babies has lost weight under their weight change, wherever it's gone. So mean 2, the group of babies that did not hear the heartbeat actually lost weight. Okay, that's not very good, is it? While the other babies who are listening to the heartbeat gained weight. And even on the basis of the t-statistic, okay, that gives us a significant value, but the Mann-Whitney test is the correct thing. Now, to do the so the effect size calculation, it tells you what to do here. It says calculate 2 plus d, which is simply the difference in means divided by the standard deviation. Tricky bit of this, of course, so the difference here is 70, isn't it? 70 grams. And the standard deviation, trouble is you've got 2, you've got 1 for each of the samples. Now you can pool these together, you can calculate the weighted average, okay, of these 2. That's one way to do it. You can pick the largest one, that's reasonable, or you can just do a straightforward average. Both of those things would be, all of those things would be acceptable. In a sense, you want to go for the most conservative estimate, which would be choosing the largest of these 2 standard deviations. Then you won't be overestimating the effect size. The correct way is to do a weighted average of these 2 numbers, okay, to produce a pooled standard deviation. So you end up with a value that is approximately 70 divided by something like 70. So the effect size, D, is approximately 1. So if you've got a number near that, you're cooking on gas. Okay, I think that's all from me today. Thank you very much.